So the first thing that I want to point out, well, maybe the first thing is like the canvas thing. I recently went through and set a bunch of late and not turned in scores to 0. Someone pointed out that one of the reasons some of those might not have been completed by some people is because I didn't set a formal due date, and so they like didn't show up on your to-do list or whatever. If you're in that boat, go ahead and do them, especially if they're non-open-ended. Those don't really have a firm deadline anyway. They have like a due date, but that's not the same as a deadline. And I don't have any set penalty for turning those in late. If I look at the end of the semester and you've like turned everything in more than a week late, maybe I'll like look at that, and if I'm supposed to let you write you a letter of recommendation, I won't be able to say you do your work on time. But otherwise, late is better than not. If it's one of the open-ended ones, go ahead and submit it, and maybe send me an email saying you've submitted it. The other thing that you'll see, if you look on the webpage for today, is a whole bunch of other material. So one of these will in fact just be a link that I'll use today in class, so I'll open that right now. The others, I've posted some additional videos going through a section of the notes that I didn't print out, which is just supplemental on remembering how polynomial division goes. So if you want a review of polynomial division, it's there for you if you want it, both as notes and videos of me going through those exact notes. Nice. So let's go ahead and get started, and we'll see where polynomial division comes up in this. Let's talk about some tricks for solving high-degree polynomial equations. And I'm going to start with some history, which will have as its conclusion that solving high-degree polynomial equations is difficult. So the first is, well, there's one type of polynomial equation that you know how to solve. Any quadratic polynomial, you know how to solve those. And that formula dates back to ancient history. At a minimum, the pyramid building age in Egypt was aware of the quadratic formula. They wouldn't have written it like that, but they were aware of the quadratic formula. In the 1540s, a mathematician named Cardano produced a cubic formula, a formula that solves any degree 3 polynomial equation. The reason you've never heard of the cubic formula or used it is because it's too big and complicated to ever use it by hand. At most, you could teach a computer to do it. But there are some good analytic things you can have a computer do to estimate solutions to polynomials anyway. That's a thing that's on the nose. After Cardano, another mathematician by the name of Ferrari produced another formula that solved any degree 4 polynomial equation. And there, the study of these sat for a while. In the 1820s, Galois, a French mathematician in his 20s, no, not even 20s, he was 19, proved that there is no general algebraic formula that solves a degree 5 or higher polynomial equation. So you can't write down the solution to a degree 5 polynomial using any combination of plus, minus, multiply, divide, or any roots. There does not exist any formula involving those that solves that, which is frustrating. It means that if you're looking for a formula that solves a high-degree polynomial equation, there isn't one. And in fact, one such equation that he showed has no solution that's expressible in terms of those ingredients is that. So even though you can't solve that equation algebraically, how would you, if you saw that equation and were asked about what are the solutions to that, what would you want to do? If you saw a graph, do you think you would see the solutions? Yeah, and you can have a computer or a graph, right? It does like a billion computations. Should have had Desmos pulled up beforehand. X to the 5th minus x minus 1. So just by looking at it, how many real solutions does that equation seem to have? 1. And it's like about there. And if you wanted better information, you could zoom in and get a better estimate. So you do have that approximate technique for solving that, but you'll never be able to find an exact formula for the solution using only algebraic stuff. How do people feel about that? So far with me? So now that we've accepted the fact that there's no single way to solve absolutely every high-degree polynomial equation, let's try to solve some high-degree polynomial equations. We'll build some tricks that will tell us partial information and work sometimes. So, the first of those tricks is the following. If you happen to know one solution to a polynomial equation, maybe you guessed it, maybe it was handed to you, we'll talk about some strategies for getting some guesses, then you can reduce the degree of the polynomial by 1 by doing polynomial long division. And so reduce the complexity of the problem to something that's easier to solve. That seems like a thing to do. Let's see that in action. So here is a polynomial equation. 2x cubed minus x squared minus 7x plus 6 equals 0. I assert that x equals 1 is a solution to that equation. Do you think we should double check that x equals 1 is actually a solution to that equation? I mean, it's easy to, right? It's easy to plug in 1. Doing that, let's see, 2 times 1 cubed is 2, minus 1 squared is 1, minus 7 times 1 plus 6. Is that 0? Awesome. Okay, so it does in fact have x equals 1 as a solution. Here's the payoff. That means x minus 1 must divide evenly into this polynomial. So that means 2x cubed minus x squared minus 7x plus 6 divided by x minus 1 is still a polynomial. We just have to find that polynomial, I guess. So how do you do that? Well, you do division. And now there are 3 things that I can do, and which of them I do depends on how you respond to the following. How do you feel about polynomial division? How many people feel positively? How many people feel like, I've done it before and I know what it's supposed to do? How many people, none of the above? Okay, let's talk about what division is supposed to mean. We'll figure out what division is supposed to do. Then we'll do it in an algorithmic way, so-called long division. And then we'll do the thing that's the most algorithmic and also the least obviously informative, and that's synthetic division. So let's just do those in order. Let's start by thinking about, we want to write this as a thing times x minus 1. So let's just see if we can fudge some things together so that factors of x minus 1 show up. That seems like a thing we could do. So let's try to do that. So here's what I'll do. And this is a very ad hoc method. I need to get a 2x cubed. But the only way I can get 2x cubed as x minus 1 times something is if I multiplied that x minus 1 by 2x squared plus some stuff. So I'll try to write down that 2x cubed so that I see a 2x, so I see an x minus 1. So 2x cubed. Let's see, if I also just saw a 2x squared, I could factor something out of that, right? I could factor an x minus 1 out. So here's what I'll do. I'll subtract and I'll add exactly that thing. Plus 2x squared minus x squared minus 7x plus 6. Do you agree that I have not changed anything? I subtracted and added a single thing? So here's the payoff. Now I see, focusing on this bit, does x minus 1 obviously factor out of that? Yeah, it's x minus 1 times 2x squared, I think. So let's write that down. That's x minus 1, in parentheses, times 2x squared. 2x squared minus x squared is x squared minus 7, let's not do that yet. Give myself space. Minus 7x plus 6. So again, I want to see an x minus 1 as a factor. If I saw an x squared minus x, I could factor out an x minus 1 as a factor of that bit. So I'll put an x squared minus x there. I can only put a minus x there if I put a plus x there? Yeah. Yeah.
X squared supposed to be negative?
So yeah, see 2x squared minus an x squared. I think it should be positive. Have I made an error? Other people check my stuff? So here's the reason that that's a plus 2. It's because I wanted this to be so I needed this x minus 1 to show up. So I needed a minus 2x squared. But that meant I had to add a 2x squared to undo that. Yeah. Cool. So same thing here. X squared. And now I need to minus an x. But to do that, I have to plus an x. So I've added and subtracted the same thing. Does that bit look like a bit that you could factor an x minus 1 out of? Yeah. So x minus 1, 2x squared plus x minus 1. This bit above, it's x minus 1 times what?
X.
Yeah, cool. And now let's write out what's left. X minus 7x is minus 6x plus 6. And now we'll just look at this last bit. I guess there should be equal signs between these because they're all supposed to be equal. Minus 6x plus 6. Can you factor an x minus 1 out of that? It is x minus 1 times negative 6. Awesome. Equals x minus 1, 2x squared, plus x minus 1, x, plus x minus 1 times negative 6. Can I now factor an x minus 1 out of the whole damn thing? Yeah, everything has an x minus 1 next to it now. Equals x minus 1 times 2x squared plus x minus 6. Oh, parentheses matter. Cool. So maybe I'll come back and see that same thing from the point of view of polynomial division and synthetic division. What do you think? Did that procedure make sense? And there were no deep ideas there. So if you like, this is the most simple-minded way to do polynomial division. It's the way that you can come up with without remembering any algorithms. You just do what seems natural until you can eventually factor an x minus 1 out. It's also the slowest way and takes the most space. But regardless, now that we have this result, let's jump down here and find the remaining roots. So we originally wanted to solve x minus, well, let's replace it with what we have. X minus 1, 2x squared plus x minus 6 equals 0. So by looking at that thing in pink, when I see two things multiplied together and set equal to 0, one of the two has to be 0. So I can break that into two simpler equations. So x minus 1 is equal to 0, or 2x squared minus plus x minus 6 is equal to 0. What's the solution to the leftmost of those two equations? X equals 1. The solution we already knew. Does the other one of those look like an equation that you know how to solve? Groovy. Let's solve it. I guess the quadratic formula is maybe the best bet. See, negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Yeah. Oh, yeah, absolutely. Sorry about that. And let me also hit this button so I have a little bit more space. Awesome. I don't know, like, that should be simplified. I don't actually care about the end result. Do people want to see the simplification gone through? Alright, how many people have just already simplified it? What is it? Oh, I didn't want to do it. I just wanted to have the answer. You know, yeah. Those two add, let's see, 6 times 2 is 12, times 4 is 48, plus 1 is 49. What's the square root of 49? 7. That's nice. Negative 1 plus or minus 7 all over 4. Negative 8 over 4, or 6 over 4. Negative 2, or 3 halves. So we found all the solutions. X equals 1, x equals negative 2, and x equals 3 over 2. Since it's a degree 3 polynomial equation, that's the greatest number of solutions we could possibly have, so we know we found them all. How did that feel? That seem natural enough? Cool. So, there are 2 other strategies for doing division. Let's just recall those strategies for doing division. They're logically the same as what's in the leftmost column. I'll just write fewer symbols more efficiently. That's the only difference. So, how do you do long division? Well, you look at the biggest term of each, and you decide what you need to multiply the thing on the outside by to get the thing on the inside. So what do you need to multiply x by to get 2x cubed? Awesome. So the first term in polynomial long division, 2x squared. Take that, multiply it by that, and subtract. Right, the same as you would do if you were doing long division. This times this, so I have 2x squared times x is 2x cubed, and you subtract, so minus 2x cubed. 2x squared times negative 1 is minus 2x squared, and then you put another negative sign, plus 2x squared. Combine those together, you end up with x squared. With me so far? Hopefully this seems reasonably familiar so far too. Good. So what do I need to multiply x by to get x squared? X. So the next term in the division is x. And notice, so far we're agreeing with what was over there. That's nice. Take that x, multiply by x minus 1, and subtract. Minus x squared. X times negative 1 is minus x, but then you make it negative again, so you add x. Minus 7x plus x is negative 6x. I need to multiply x by negative 6 to get negative 6x. And now, anyway, negative 6 times x is negative 6x, but you need to subtract it, so you do plus. And just like long division, the remainder might not be 0, but I knew in advance this would divide evenly into, so the remainder had to be 0. So that was fast. How many people would like to see more examples of polynomial long division happening? There is a recording posted to the webpage in which more examples of polynomial long division happen. I'll suggest that you start there. Otherwise, come by my office during my tomorrow extended office hour and talk about polynomial division. But there's the algorithm. There's also a section in the book that's worth looking through in the appendix. So, this took fewer symbols than that to write. But this required you to have like an algorithm memorized. This didn't. So there's the trade-off. Synthetic division goes one step further. You didn't really need to have like the x's written at all, did you? Like you could have remembered that. This x, you didn't even really need that. You just needed to remember there's an x there. So what synthetic division says is take that minus 1, put it there as a 1, and do the following. First, take that 2, and just write it there. And it's not going to feel motivated at all what I'm about to do. We'll get the right answer, and then we'll talk about why we got the right answer. I'll take that 2, I'll multiply it by the 1, I'll write that underneath that -1 in the next column. I'll add these 2 together, and I get 1. I'll take that 1, and I'll put it here. 1 times 1 is 1, so I'll draw a 1 in this next column. Plus. -7 plus 1 is -6. So I'll take that -6. I'll draw it here. -6 times 1 is -6. 6 minus 6 is 0. So maybe I'll put that remainder equals 0 just to make sure that I write that there's a remainder of 0. So now I have to interpret this result. This means 2x cubed minus x squared minus 7x plus 6 equals 2x squared plus x minus 6. So you just read off these things as the coefficients after you do the division. So, on the one hand, while I was doing that, you had no idea that I was doing division while I was saying those words, unless you already knew that I was doing division because I just did it. On the other hand, that took up like no space and also didn't take very long. So, there's the upshot of synthetic division. As long as you're dividing, well, something got erased. So this requires that the divisor is x minus a constant. There's the assumption in synthetic division. And that constant is what goes here. Groovy. So, once you do polynomial division, however you do it, you can reduce the complexity of the problem by 1, make the problem easier to solve. How do people feel? Pretty okay so far? So, there's trick 1. Once you know a solution, you can do division to reduce the problem complexity by 1, hopefully to something that's easy enough to solve. I think it's worth spending time to do one more example, and it'll be one of those two. So let's either find all the solutions to x cubed plus x squared plus x plus 1, or all the solutions to 2x cubed minus 10x squared minus x plus 5 equals 0. How many people would rather see the first one done? How many people would rather see the second one done? All right, let's do the second one. I assert that x equals 5 is a solution. Should we check that 5 is actually a solution? Yeah, I mean, you can't trust that I do anything right. So here's how I'll advocate doing it. So we certainly could do it by hand. I am, however, going to say, well, there will be enough computations that we'll do that I'm going to try to get a computer to do it. So here's what I've done. I've pulled up a command in Wolfram Alpha to evaluate a polynomial at an input. So let's write down that polynomial and that input. So let's evaluate 2x cubed minus 10x squared minus x plus 5 at x equals 5. Not x equals g. All right, there it is. The result is 0, so we're good. So, now that we have that, let's find the rest of the solutions. So we need to do division, and there are like 3 ways. We can do like the factoring by grouping ad hoc way. We can do long division. We can do synthetic. What preferences do people have? Ad hoc, long division, synthetic division. All right, I'll do synthetic. So, let's see. So I know that x minus 5 is a factor. To figure out what the result of division is, I'll just put a 5 there. I'll see how many times that divides into 2, -10, -1, 5. And I'll follow the algorithm. Those of you who would rather do long division, go ahead and do polynomial long division. We'll see if we get the same thing. We should. So what's the algorithm? Take that 2, draw it there. 2 times 5 is 10, so I'll put a 10 here. Negative 10 plus 10 is 0. So I'll draw a 0 there. 0 times 5 is 0, so I'll put a 0 there. Negative 1 plus 5 is, negative 1 plus 0 is negative 1. So I'll put a negative 1 here. Negative 1 times 5 is negative 5, the remainder is 0, it checks out. So what does that mean? That means 2x cubed minus 10x squared minus x plus 5 is equal to x minus 5 times 2x squared, no x's, minus 1. All right. That feel pretty okay? Groovy. But that's not done, right? What did this question actually ask us to do? We wanted the solutions. We factored it though, so that's like really good. Let's set that equal to 0 and solve. All right, what are the solutions to that? Well, alternately, do people want me to talk through how to find the solutions? Okay, tell me the solutions to that equation. Yeah.
I had 5 positive square root 1/2 and negative square root 1/2.
You are correct. There's only one simplification that I'll make. So I won't like seeing a fraction under a square root. And I won't like seeing a square root in the denominator. So I'll rewrite those a little bit. That's a correct answer. My only complaint is simplify. So I would simplify the square root of 1/2 to be the square root of 1 over the square root of 2. Well, 1, I know the square root of 1. It's 1. So I can replace that with a 1. And then I'll play the game where I multiply and divide by a thing to make the denominator into something that doesn't have a square root. So I'll multiply and divide by the square root of 2. That seems like a sane thing to do. Let's do that and see that it actually helps. That's 1 over root 2 times root 2 over root 2. The numerator is now root 2, and what is the denominator? 2. So it'll be the square root of 2 times the square root of 2, so it's the square root of 2 squared, which is 2. So that's how I would prefer to see that written, but that's a really minor simplification. So, low priority thing. All right, so we can make it, if you have a solution to a polynomial equation, you can simplify the polynomial equation by 1. Hopefully you can do that enough times to get down to degree 2, because then you can use the quadratic formula. But there's something not satisfying about that. So it says in order to solve a polynomial equation, you have to have some solutions to that polynomial equation. So this is where our second trick is going to come in. It's not going to tell us any definite solutions to a polynomial equation, but it'll give us guesses. It'll give us a complete list of all of the candidates to be solutions to a polynomial equation in the rational numbers. So here's what the rational roots test says. The rational roots test says that this polynomial equation, so there it is, there are some coefficients next to powers of x. If that has a rational number as a solution, something that looks like p over q, then, color code a little bit, the numerator p must divide a0, the denominator q must divide the leading coefficient a sub d. So let's just write that out in plain English. So it says that the numerator divides into the constant term, numerator being the fancy word for the thing on the top of a fraction, and the denominator, oh, my color coding is exactly backwards. That's really annoying. I mean, it's too late to do any better than absolutely backwards, so that's what I'm going to do. The denominator, oh, yeah. The denominator divides evenly into the leading coefficient. So the reason that the rational roots test is true isn't that sophisticated. It's true for the same reason, really, that the square root of 2 is not a rational number. The reason the square root of 2 is not a rational number is you actually apply the rational roots test to the equation x squared minus 2. You check what the roots of that could be according to the rational roots test, you find that they aren't, and so it doesn't have any rational roots. So let's apply the rational roots test to this polynomial to get a finite list containing all candidates to be rational solutions to that polynomial equation. No promises that any of them will be, they're only candidates. So let's see. So if you want to apply the rational roots test to this, then the numerator p has to divide evenly into which number? The constant form. And what is the constant form? Yeah, it is, I guess, -6, but dividing into -6 is kind of the same as dividing into 6. So I'll ignore that sign for now. So P divides evenly into 6. How many people have seen a vertical bar for divides evenly into before? Okay, well now you have. That's just a shorthand for P divides into 6 evenly. Or alternately, P is a factor of 6. Oh wait, how many factors does 6 have? Not that many. What are the factors of 6 is maybe a better question.
1, 2, 3, 6.
So P is one of those things. That's not so many. It's only 4 things. Now Q. What does Q have to divide evenly into? The leading coefficient. And what is that in this case? So Q is a factor of 2. Oh, but I know the factors of 2. They're only 1 and 2. Groovy. So now we can list all the possible values for plus or minus P over Q. So let's see. It could be 1 over 1. That's 1. 2 over 1 is 2. 3 over 1, 6 over 1, 1 over 2, 2 over 2, 3 over 2, 6 over 2. So right now it looks like that's, what, 8 times 2 is 16 candidates? Is there any redundancy in this list, though? Yeah, what things can I erase because they're already on the list? 6 over 2, because that's already there as 3. What else?
2 over 2.
2 over 2. That's a really poorly drawn 2 over 2. That's 1. So really there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6 times 2 is 12. There are 12 candidates. Oh good, so that means that there's no reason to even try plugging in like x equals 7. 7 is not a solution to this polynomial equation because it's not in the list. Those are the only possibilities. No promises that any of them are, but nothing else is allowed to be. How do people feel about that? So, what do you think? If I wanted all of the rational solutions to this polynomial equation, what would you do? Yeah, plug in those. If there are any solutions, they're on that list. And 12 isn't that huge a number of computations to do. And I guess, let's give some options. Well, you know what, there are columns of you. Plug in plus or minus 1. Plug in plus or minus 2. Plug in plus and minus 3. Plug in plus and minus 6. You're allowed to use a calculator. For the people doing plus or minus 1, you could probably do it faster without using a calculator, but I understand if you're going to use it anyway. And as soon as you have a result, let's see, it has an equal sign there, so let me know what number I should put in which spaces as soon as you get one. Especially if you compare it with someone next to you and you get something the same, then that means you're probably right. Yeah.
Sorry. Plugging plus or minus 2 be 0.
Okay. I guess that's all we care about, so maybe I won't write down what they are, I'll just write not equal to 0.
Oh, I mean, I have the answer.
Yeah. Sure then, what are the values?
So the top one is 40, and the bottom one is 36.
40, 36, but as you say, the main thing is none of those are 0. What other entries can I fill in?
Negative 3 and 3. Negative 3 is 60 and 3 is 126.
Alright, so far no luck? Yeah.
1 is a raised and negative 1 is 10.
Say 1 again?
1 is true.
Oh, excellent. Okay, cool. So we know a solution. There is a solution.
Negative 6 is a solution.
Negative 6 is a solution. That's good. How about 6? Okay. It's probably some like silly big number. So I guess that leaves 2 of them left to plug in, and I guess if I had you do some computations, maybe I should do a computation. I think I've cheated to make it easy for me to do that, though. All right, so there's the polynomial I wanted to check. Is 3 halves a solution? No. I guess I'm doing the mode of order. It's now easy to plug in negative 3 halves. Is not a solution. Negative 1 half. Negative 1 half appears to be a solution. Do I even need to plug in a half at this point? Yeah, 1 half couldn't possibly be a solution because how many solutions are there allowed to be? 3. How many have we found? So we're done. So, which of them are actual roots? It appears as though x equals 1, negative 6, and negative 1 half are roots. And in fact, those are all of them. Can't be more than 3. So these are all of the solutions. Groovy. So, yeah, let's do one more. 3x cubed plus 2x plus 2 equals 0. I think I'm going to shut up for a second, and we'll come together once we get down to what are the possible rational roots to this thing. Give me a complete list of those, and then we will test them. Cool. So once you have that list of roots, compare them with someone around you if there's someone convenient around you to compare against. All right. So let's come together. What are the choices? What are all the P over Qs?
Plus minus 2. Plus minus 1 over 3 and plus minus 2.
Cool. I agree. Does anyone want me to go through the discussion? Okay. Cool. So I guess there are 8 things there. Let's check which of them are actual roots. And so maybe what I'll do is plus or minus a third and plus or minus 2 over 3. I'll leave it to you all to do plus or minus 1 plus or minus 2 real quick. So 1 over 3. Oh, by the way, so the link to this is on the webpage right now. I've given this as a useful Wolfram Alpha link, which I encourage you to use at your convenience. If you have other computational tools you like, use those. So, 1/3 fails.
You check the equation.
Oh, this isn't the right polynomial, is it? I have to change that too. Thank you. That's embarrassing. 3x cubed plus 2x plus 2. All right, 1/3 still fails, but this time it actually fails as opposed to just me doing something over. Plug in negative 1/3. Still fails. Negative 2/3. Still fails. 2/3. Still fails. Okay. So that's a complete checking of those last 4 really roots. But what about the first 2? Are any of those roots? No. So what conclusion can you make?
No actual solution.
So you picked up on that one, actually. So none of these are solutions. So one conclusion you can make is this has no rational solutions. Any solution that this polynomial equation has must be irrational because those will have all of the possibilities to be rational solutions and none of them will. All right, so we're stuck. We don't have like any initial guesses to solve this polynomial equation. Okay. Well, what strategy do you always have in your back pocket? Something you can do. You have a quadratic equation. People are like hacking, but I have a few minutes, right? So, well, wait. You said quadratic equation. Do we actually have that strategy here? Is this a quadratic equation? No, it's cubic. So I agree with you too quickly. What's a strategy to approximate roots that you have access to always?
Division.
Well, what are you going to divide by? You can factor by grouping, but you need like a guess, right? It's like you're kind of screwed in terms of any of those exact strategies. Could you look at a graph though? Yeah, that's what I was trying to get at. So we don't have any of these fancy tools, but you can read off information from a graph, kind of always. So you could graph the thing. I think I won't right now. I'm going to mention the third tool before moving on, and that's Descartes' Law of Signs. So, René Descartes, the same mathematician as for whom Cartesian coordinates are named, and to whom is attributed the line of reasoning, I think, therefore I am, has the following law. So if you have any polynomial Px, you can get an idea of how many positive or negative solutions it has as follows. The number of positive solutions to P of x is equal to 0 is equal to the number of times the sign of the coefficient changes, or that number minus something even. So let's maybe apply that to this previous example. Let's think about the polynomial 3x cubed plus 2x plus 2 equals 0. So the powers are written in descending order. We'll count how many times the coefficients change from positive to negative or negative to positive. From 3 to 2, did that change from positive to negative or negative to positive? From 2 to 2, does that change? So does the coefficient ever change signs? So here is a conclusion. This has no positive roots. If you plug in any positive number, guaranteed, you will not get 0 out. Oh, so that could actually have saved us some computation on the previous page, right? Some of those candidates were positive. That tells us in advance that they had to fail. You can also use this to get information about the number of negative roots, because a negative solution to an equation is the same as a positive solution to that. Right? If that has a positive solution, then take that, make it negative. That gives you a solution to the original. So if you do that, you get negative 3x cubed minus 2x plus 2 Does the sign ever change from positive to negative or negative to positive? Yes. How many times? Once. So this has one negative solution. And we'll come back to that, this thing, this doodad, next time. Now I've used up all my time. I let y'all end a little bit all at once, and you just assume that I'm going to stop at a reasonable time instead of using all my minutes.